So, hello everyone. Today I want to discuss some examples of important groups because often in exam they ask question regarding give example of a group which satisfies certain property. Like for example, once they asked give an example of infinite group, where every element has finite order. Okay, so in the exam, if you're not very good with model algebra, you might face difficulty in thinking examples at that time. Okay, so we will discuss some examples of groups, some important examples that we should know and which help us create like more examples. Okay, so the first example that I want to take is, which is a very important group, very important group, is your client for group. Okay, is your client for group. Client for group. This group is very special. Okay, what is a client for group? So this has 4 elements. That's why client 4. Okay, so K4 actually, if I write it is A, B, C, where E is the identity. So it has a very good property of A square equals to B square equals to C square is equals to E. Okay, now if A square equal to B square equal to C square equal to E, it means that A inverse equals to A, B inverse equals to B, C inverse equals to C. That is, every element is self-invertible. That is, it's inverse of itself. Self-invertible. Now there is the question also, theorem also. It says if every element is its own inverse, then show that it is a abelian group. If every element in a group is of order 2, then show that it is an abelian group. Okay, so you can prove that it is an abelian group. Okay, so the question is that show that in a group, if every element has order 2, then it is abelian. Okay, right. So you try this question. It's a very easy question, but you should try. Why client for group is very special? Okay, what is the importance of client for group? The importance is K4 or the client for group is smallest non-cyclic abelian group. Abelian group. Okay, smallest non-cyclic abelian group. That is, your K4 group is abelian, but it is not cyclic. Okay, so we know that there is a theorem which says that every cyclic group is abelian. Okay, but converse is not true. That is, every cyclic group is abelian, but every abelian group need not be cyclic. Some abelian group may be cyclic, some may not be cyclic. So if I have to give example of, let's say question comes for 15 marks that prove that every cyclic group is abelian. Also, is the converse true? So you can prove every cyclic group is abelian, very easy to prove. Then they are asking, is the converse true? So you will say, no, the converse is not true. And you can give client for as the counter example. So you should prepare these kind of counter examples. Okay, you should prepare these kind of counter examples. So this is a very important group. Why? Because this is the K4, client 4 is the smallest non-cyclic abelian group. Okay, so it is non-cyclic but abelian. This should be known to you. Okay, now group 2, very important group, is your quaternion, which is your Q8 group. Very important. Okay, so what is the property of Q8 group? So Q8, it has your elements as your 1. Okay, then your minus 1 is your element, then your I, okay, plus minus I, plus minus j, and plus minus k. These are total 8 elements. 1 2 2 2 2, total 6 plus 2, 8 elements. The property in, okay, such that I square is equals to j square is equals to k square is equals to minus 1. That is, they behave like iota, and I into j is equal to k, j into k is equals to your I, okay, and k into I is equals to your j, and your j dot I will be your minus k, okay. Similarly, so actually, if you remember the vector product, it is like that. This is, okay. So I into j will give you k, k into I will give you j, and if you go, okay, anti-clockwise, sign will change. K into j will give you minus I, like that, okay. So this is the, now what is the importance of this group? So if you see, because here, if I take any two elements, I take I and j. So I into j is equals to k, but j into I is equals to minus k. So here I dot j is not equal to j dot I, right? Therefore, Q8 is not abelian. Q8 is not abelian. So the quaternion group is a non-abelian group. It is a non-abelian group. But why are you studying it? What is its importance? Because it has some proper subgroups. Okay. Okay. So total number of elements are 8. What can be the order of proper subgroup? So by Lagrange theorem, we know that order of a subgroup divides the order of the group, right? So order of subgroup can either be your 4, because, so let's say S is a subgroup, so an order of subgroup will divide it. So order of subgroup can be either 2 or 4, 8 or 1. 8 or 1 I'm not taking, because 1 means your identity element only, and your 8 means that it's the group itself. So proper subgroup will be of order 2 and 4. So let's say order 4. Okay, order 4 subgroups. So if you see, the order 4 subgroups are your S1 is equals to 1 minus 1 I minus I. Okay, your S2 is equals to 1 minus 1 J minus J, and your S3 is equals to 1 minus 1 K and minus K. Okay, if you see, S1, S2, S3 are cyclic in nature. Cyclic in nature. Okay, you can see that, because K, then K square is equals to minus 1, then K cube is equals to minus cube, K की power 4 is equals to 1. So the K generates your S3. Similarly, I will generate your S1, J will generate your S2. Okay, so S1, S2, S3 are cyclic in nature. Okay, let's say the order 2 subgroup, there is only one subgroup of order 2. Okay, this is your S4, 1 and minus 1. Okay, 1 and minus 1. This is your subgroup. Here also, minus 1 square is equals to 1. Okay, so here, this is also a cyclic. This is also cyclic. This is also cyclic. Okay, this is also cyclic. So you can use it as, what is the importance? As counter example for first counter example is Q8 is a group. Q8 is a non-abelian group where subgroups are abelian. Okay, Q8 is a Non-abelian group where subgroups are abelian. Why? Because all the subgroups are cyclic and every cyclic group is also abelian. It means all the subgroups are also abelian. So Q8 is a good example of a non-abelian group such that the subgroups are abelian. So if a question is asked, give example of a group which is a non-abelian but has abelian subgroups. Second thing is Q8 is non-abelian, and non-abelian group can never be cyclic. It means non-cyclic. But subgroups are cyclic. But subgroups are cyclic in nature. Subgroups are cyclic in nature. Okay. So this is another very important example that you need to remember. Q8, quaternarian group. Okay, because this is the example of a group which is itself non-abelian, non-cyclic, but has cyclic, abelian, okay, subgroups. So this is another example. Okay, and now come to the third group. Okay, what is the third group? Okay, infinite group with elements of finite order. Okay, infinite group with elements of finite order. So very famous group that you will find in, if you Google it, you will find the example of such group is Q by Z. Q by Z. So Q by Z will be of the form your P by Q plus Z, right? Of this form. So why this? So because there are infinite number of rational numbers where Q is your rational number. This is your rational group of rational numbers, and Z is your okay, Z is your additive group of integers. Okay, integers. Okay, additive group of rationals and additive group of integers. So P by Q, this is the quotient group. This is a quotient group of. Why this is infinite? Because P by Q can be infinite. Okay, I can write 1 by 2 plus Z. Z means the whole spectrum, the whole collection of integers. Okay. Okay. 3 by 4 plus Z. And like this, I can create infinite elements. So this Q by Z has infinite number of elements. Infinite number of elements. But any element will be of the form P by Q. Right. Now, if I add it Q times, okay, so it will be P by Q plus P by Q plus P by Q, okay, plus Z Q times. Okay, let's say this is Q times. This will become your P plus Z. Q will cancel out. And because P is also an integer, so it will get absorbed because of this is a property of cossets. So this will equal to Z only, which is the identity of the group. It means the order of P by Q plus Z is Q. It is every element of this group has order, finite order. But okay, if it is 1 by 2, the order will be 2. 3 by 4, order will be 4, like this. So there will be finite order, can be very large also, 1 upon some prime number, but it will always be finite. But because people are not very comfortable with quotient groups, especially people who start, for them this becomes very difficult to remember. Okay, so let me give you an easy example of the same property. Okay, consider a group of polynomials with coefficient from Z2. Z2 means 0, 1. That is any number modulo 2. So what is the property of Z2? Z2 means that 1 plus 1 is equals to 2 mod 2, which is equals to 0. Okay, because when you divide 2 by 2, remainder is 0. So this is the property. Now, if I take any polynomial, let's say x square plus x, and I add in that x square plus x again, it will become 2x square plus 2x, which is equals to 0x square plus 0x, because 2 is 0 in Z2. This is equals to 0, which is the identity. So what is the order of the polynomial? Order of the polynomial is 2. Order of polynomial is equals to 2. Order of polynomial is equals to 2, right? So this is a very simple example of a group, because there can be infinite polynomials, right? You can write infinite polynomials. You can write x to the power 4 plus x plus 1. You can write x to the power 6 plus x to the power 4 plus x plus 1. You can create as many powers as you want. And therefore, the group of polynomials with coefficients from Z2 is a group with infinite element. That is, it has infinite order. But every element in this group will have order 2 only. That is finite order of 2. Because when you add them together, their answer will always be, okay, 0. Why? Because coefficient can either be 1 or 0. Okay, if coefficient is 0, nothing to add, nothing. Okay, if then coefficient is 1 plus 1 will always give you 2, and 2 becomes 0 in Z2. So this is another, okay, important group. So what we discussed today is, okay, let me summarize. First we discussed, okay, that K4 Klein 4 group. Okay, Klein 4 group. Why it's important? It is the smallest non-cyclic but abelian group. Non-cyclic abelian group. Non-cyclic abelian group. Second thing we discuss is your Q8 group. That is quaternion group. Why it is important? It is your non-abelian group, hence non-cyclic also. Non-abelian, but its subgroups are cyclic. Cyclic means abelian also. Okay. So this is, and the third thing that we discussed today is that group with infinite order having elements with finite order. Okay, that the group has infinite order, it has infinite element, but every element has a finite order. So we studied 2 examples. The first example was, you can take q by z, okay, which is equals to your p by q plus z. Okay, and the second example that you can take is, okay, z2x, that is group of polynomials over Z2, that is over Z2 means that is coefficients belonging to Z2 over addition. Operation is addition. Okay, so these three, there are more such groups. There are 8-10 groups that you should remember. Okay, like you should know about the S3 group, you should know about, okay, so there are 8-10 groups that we have to remember. Okay, so like for example, many questions in UPSC has been asked on the property of dihedral group. They have never named it dihedral group, but they will give you the properties of dihedral group and they will ask you how many elements are of order 2. Okay, so that is a very easy question. If you can identify that this group is a dihedral group, you can easily do it. Okay, using the property of dihedral group. So we will discuss dihedral group in our coming lectures also. So in the end, make a list of important groups at one thing, and then we will also see some important properties of groups, normal groups, subgroups. Okay, all these things. Okay, so have a good day. Bye.